Now that we have some examples of infinite series, infinite summations under our belt, let us go a little bit further and talk about a special kind of series called a power series. So what we're going to do is we are going to specify just a list of numbers we're going to add up. And the formula we're going to use has two different things going on. We have some real number x, which we are raising to the nth power. And we'll have a list of constants here, starting at n equals 0. We'll have C0, C1, C2, C3, C4, and so on. And when we go to compute the series, right, we'll have C0 plus C1 times x plus C2 times x squared plus C3 times x cubed, and so on. So these almost look like polynomials, except that polynomials are finite. Polynomials have a largest power of x. So again, these are called power series. And if x is a particular real number, then we can test this series, determine whether or not it converges. We should be able to get some real number as the value of this infinite sum. Now, whatever that number is will change depending on what value of x we try to evaluate the series with. So I could build a function. All I need to define a function is just a rule for inputs and outputs, where f of x is just going to be the value of this series so long as the series converges when I use that particular value of x in my formula. So we've actually already seen something like this when I discussed the rule for working with geometric series. So if all the coefficients are equal to 1 for all n 0 and up, then this looks exactly like my geometric series. I start off with 1, I add x squared, I add x cubed, and I just keep going. And so we've already talked about how this geometric series will converge depending on the value of x. Previously, I talked about this formula using r for some common ratio. But if I'm thinking about this as giving me a number which depends on my input, it's a little bit more traditional to use x's instead. Your variable names can be whatever letter you like. We're just following convention. So this series will converge, but only as long as x is small enough. X has to be between -1 and +1. And it will be, and the series will diverge if x is any larger than that, in absolute value, of course. So if you haven't already, get very used to thinking of things in terms of their magnitude rather than their, like whether they are positive or negative. Okay. So in general, if I have a power series, maybe I can shift my x over by some amount, right? I can do this for functions, so I should be able to do this for series as well. If I want to shift my function, graph my function over in one direction, I just subtract that amount off of my x. So I can do that in the series as well. I'm just going to replace x with x minus a. every single time it shows up. So this series starts, we'll have C0. We'll add C1 times x minus a, and we'll add C2 times x minus a squared. Then we'll add C3 times x minus a cubed, and so on. And this has a special name where we're going to call this the power series centered at A, the power series about A. So what's going on here, just like when we shift the graph of a function left and right, we are changing which x coordinate behaves like 0. So in this formulation, the number A will behave like 0. And for all of this to make sense, we are going to say that anything to the 0 power equals 1. So just like if I have 0 things added together, that's going to make 0. If I have 0 things multiplied together, that will make 1. Okay. So given one of these series, how do I know where the series converges and where the series does not converge? That's pretty important information. All I have to do is use the tests that I already know. I know lots of tests for convergence of a series. So let's take a look at a series whose coefficients are n factorial. So the coefficient of x to the power n will be n factorial. And if I want to check this for convergence, I'm just going to run, say, the ratio test. The ratio test says take the quotient of successive terms in your sequence in absolute value. So here the limit as n goes to infinity of the absolute value of my n plus first term in the series divided by the nth term in the series. Well, that's going to look like the absolute value of n plus 1 factorial times x to the power n plus 1, all on n factorial times x to the n. So I get my cancellation as usual. And this limit will look like the limit as n goes to infinity of n plus 1. Since positive whole numbers are positive, I don't need absolute value bars there. I don't know what value x is here, so I still have to keep my absolute values for my x. And actually, it doesn't matter what number my x is. This limit is going to go to infinity, right? This is n plus 1 is going to infinity. Unless my x equals 0, this limit diverges. And the ratio test tells me that the series is divergent. The series does not have a number I can associate it to. Now, if x equals 0, I just have, well, 0 factorial is 1. Again, the product of no things is 1. And then I'd have all the later terms, say 1 factorial times 0 to the power 1, 2 factorial times 0 to the power 2, and so on. Those will just be 0. So this series, this power series, only converges for x exactly equal to 0.